So this is Module 3 in Lecture 19, a survey of recent deep neural networks. And we are finishing the Section 3 after this lecture. So in this lecture, we give a very rough, quick survey about DNN, and we kind of chunking the DNN landscape literature according to 7 variables. So in the module 1, we use the data variable and F, like network representation, F architecture variable to chunk the literature. And we covered the CNN, transformer, graph NN, and neural Turing machine, and the data and the network representation are actually very correlated. Then in module 2, we covered 3 new tasks. So that goes beyond the supervised prediction task in the previous session we covered in this class. So the 3 tasks we covered, the new tasks are generation task, reinforcement learning task, and the learning to learn task. So now in this module 3, I will focus on using this third and the fourth variable, essentially trying to tell you something very good happening now, trying to do a better training of the model. So there are many ways to train to get a better model from data. So you can have new laws, you can have new optimization and new tricks, and also consider coupling with the underlying parallelization like architectures. So in this specific module 3, I will focus on 3 new optimization pipelines. So more specifically, the first pipeline is this self-supervision, or like more specific, the autoencoder or other type of self-supervised laws guided unsupervised pre-training pipeline. So this really is a great pipeline to learn better representation. The second pipeline is this Generative Adversarial Network GAN pipeline. That it's a very novel, very great pipeline or workflow to get better better generated samples, generation of samples. And then the third pipeline is this called AutoML pipeline, trying to learn the hyperparameters, to learn the best the network architectures. All right, so let's get started. So the first pipeline is this Layerwise pre-training pipeline. And specifically, it's kind of always use a lot this kind of self-supervised laws to do Layerwise pre-training. So we already mentioned about autoencoder decoder workflow in the dimension reduction lecture. So essentially, we have the X input. We try to mostly convert it into a lower dimensional hidden space, like H space, H vector, which it's H. It's this a hidden layer representation, and then using this hidden layer H to like project to get the other output, which is X predicted. So essentially, we try to minimize this input X and the predicted X hat, and using this called reconstruction loss, and plus a lot of many different kinds of regularizations to push this hidden layer representation to become a good and reliable feature detectors. And there are many variations of autoencoder decoder workflow. So for example, you can have this variational type of VAE, and you can also have this adding noise in the input and called denoising AE, DAE. You can also add sparsity on this hidden space called sparse autoencoder decoder. And also in this graph, in this slide, everything is more feed forward MLP encoder, both encoder and decoder, but you can replace them into a convolution or stacked convolution, right? So in this case, we can have like especially the last figure is the encoder is a convolution formulation, and this decoder is a convolution based, which is called deconvolution network architecture. So encoder is convnet, decoder is deconvolution net. So this together is a deep convolutional inverse graphics network. So it's of course, there's some other nuances here, but basically it is using this autoencoding decoding workflow, and the submodules are the convolution and deconvolution based. So we talk about this reconstruction loss and the variance of this reconstruction workflow. You can actually use this to do many other things. So for example, you can, assuming you have many layers, you can try to use that workflow to train the first layer first, and then second layer, third layer, fourth layer, so on and so forth. Each layer can be trained well first with some type of self-supervised loss. So in this case, we just told you about reconstruction loss, but there are many other kinds, like constructive, very popular recent loss function people kind of try a lot is this constructive type of loss function. There are also recent like mutual information maximization based. So there are actually a lot more other kind of pairwise ranking based, so on and so forth. So basically, it is just designed to force to learn good features that in every layer to describe what comes from the previous layers. So this type of unsupervised feature detection, it's using in this workflow normally called unsupervised pre-training. So you use original data and you try to train each levels of the model in a greedy way, and then you do just work bottom up to train first hidden layer, fixed parameter, then train second layer, fixed parameter until you train nth layer, and then fix its parameter. And then you use label data to train the following using those unsupervised you just trained. And then you refine the features by back propagation so that they become tuned bias towards your current task. So this is called supervised fine-tuning after this unsupervised pre-training. And this is a very powerful workflow, has been proved to work very well to improve many of the supervised prediction tasks. So this is the first workflow we want to cover: pre-training and this fine-tuning of DNN layer by layer. So essentially, it's trying to solve the issues in DNN model training caused by two challenges, because non-convexity of the loss function, also this vanishing gradient issues because of this really deep structure. And this layer-wise pre-training can help with both challenges. And there are also other, not just unsupervised pre-training, there's also supervised pre-training we don't cover here. Feel free to check out by yourself. So essentially, it tries to learn features at different levels of abstractions. And this is a very powerful workflow. All right, so that's this unsupervised layer-wise pre-training workflow. And then now let's talk about a very novel and powerful generation workflow, which is called Generative Adversarial Network, or in short, GAN. So this is ranked as 10 breakthrough technologies in 2018 by MIT Technology Review. And so essentially, there are like two models here. So it's the G model and the D model. So G is this generation model. D is a discriminative model. So G is used to generate samples. So G is by some kind of hidden or noisy representation Z, and G is used to generate the X. So in this figure is to generating a face. And then we are feeding this X generated into a discriminator. So this is the same discriminator. So these are two. So you're feeding the samples, like this is the true face that's from the observed samples to this generator. You're also feeding this generated samples from your generator to this discriminator. Basically, you're trying to learn both the generator and also discriminator. You try to make a really, really good discriminator that can distinguish generated data and generated faces and true faces. And also you try to make your generator to generate those faces that your discriminator just cannot distinguish. Is it from the true data or it's from the generated sample? So essentially you are trying to make a really, really great generator that a really good discriminator cannot distinguish your generated sample versus the true sample, which essentially means what? It means your generated sample is as good as those samples sampled from the observed data. So this is a very novel workflow and largely improved the generated samples quality. That people start to use this GAN workflow in many different type of applications. So for example, this is a very classic application. It's like a style transfer. So you have this actor's face image, and then you feed another pair cartoon, like also a face kind of sketchy. Then you want to make this a cartoon style of the actor image, and so this is actually the generated style, generated a cartoon style of the actor's face image. And this architecture uses a generator and also a discriminator. And this is the GAN part, right? A generator and a discriminator. And at the same time, if you look at this, and this essentially is like a convolution, if I remember correctly, I think this is a convolution to get the hidden representation, then from the hidden representation to regenerate the image. So the G itself, it's kind of autoencoder decoder formulation. And then this hidden representation is also used in a reconstruction. It's also kind of regularized by a reconstruction type of loss. So this is a combination of GAN workflow and also that self-supervised reconstruction workflow. And it generated really great, like kind of style transfer images that was not possible before. And then there's also all these other kinds of impressive applications. Like in this case, you try to style transfer this texture from the zebra to the horses. You try to style transfer the summer style of the views and into a winter style of the views. And then especially on the face, human face, and this is a very important work, like a milestone of GAN called progressive GAN, and basically this makes the face image generation to have higher, very good quality and stability. And so this kind of generating the face images at all these different resolutions. So that's why it's called progressive GAN. And then last year in CVPR 2019 and from NVIDIA, there's this really impressive work called the style GAN. So we can see, so this first row is the source B image, and the first column is this source A image. So you can think about this as a matrix combination. So every image in the middle is a combination of style from the source B and the source A. So let's look at this image. So this woman's image is generated from the hair, more like from up this young girls, and then this women's like it's more like a combination, and you can actually tell, I mean, it's a relatively really nice combination. And let's look at this baby, this baby's this baby boy's face, and then with this girl, and then it's kind of generating a toddler girl's image, face image, which looks very, very real. And this boys, and then it's a combination of this women and these boys. I mean, so it's really impressive and with very nice quality. All right, so yeah, so this may make you realize what we covered in these tasks. I think in the second module, in the generation module, we covered DeepFake, right? So a lot of the DeepFake tools relied upon the style GAN or something related to the GAN type of style transfer, or this the GAN-based workflows for the generation. Okay, so that's the second workflow for a better generation. And now let's jump to the third workflow, which is for, it's called AutoML in general. It's for a better optimization, a better search. So during at the homework 3, students have asked, so how do you know how many layers, how many hidden units, what's the kernel size, what's the stride size when you're doing the design? When we handle that fashion MNIST data, right? So we actually mentioned, I mean, it's the deep learning engineer's job to design that in that homework. Yeah, so yes, that's kind of partially true until this type of AutoML workflow comes out. So essentially, this kind of AutoML workflow proposed something called a controller. And this controller, the controller is to output, to predict how many filters. In a filter, what's the height? In a filter, what's the width? What's the stride height? What's the stride width? What's the just all those parameters, hyperparameter you have to set, the topology you have to design. And this are all modeled as an output of a deep neural network. And think about, and this is a higher level task. So your lower level task, assuming is image recognition task, and you're trying to design a conv net, right? And then you have to design how many layers of conv blocks, all those different kind of choices, right? And then we can think about there's a controller neural networks give you really good guidance, and then you can use the output from this controller, then set a fixed network topology, and then you just use that topology and the hyperparameters and use your data then just to learn the weights. So essentially this is a meta formulation, right? So I need to learn higher level a good controller. After the controller has good output, I use that output to have a fixed topology, and then I use my data to learn better weights. So it's a very good design to learning the topology. But it's also very costly. Yeah. All right. So similar ideas, and then it's also being used in this paper is to learn how to optimize. So again, kind of controller idea. You have a controller, then your controller's output is those decisions you have to make to select what type of optimizations. There's so many smaller things in the optimization choices, right? And you can just use this controller to predict those choices. So this together, it's all in this regime called automated machine learning, AutoML. Okay, all right, so we finished the module 3, and now we move to module 4. So in module 4, we talk about new metrics, new adaptation of the deep learning models. Great. So we finished the current module, and this specific ending clip is recorded after I finish all the 4 modules, and I realized my nutshell index page doesn't have the module segmentations. So here it is. So this page is better displaying how the module are related to the different elements of the nutshells, and also inside each module, and how are the topics, trend topics we selected. Okay, so great. I hope you enjoy the content and see you in the next module.